Here's another two-train math problem. If you can solve this problem, people will think you're a genius, but it's actually super simple. You just have to have somebody show you how to do it. I just did a video on a two-train math problem, and in that video, both trains had a known location. There's train A and train B. Both had a known location in that video. In this video, train A is the only one with a known location, and we have to decide where we're going to put train B so that both train A and B can meet up at the same time at the train station. Here's a situation. These are not commuter trains. If they were, then their goal would be to get to the train station as fast as possible. But these are just sightseeing trains or tourist trains. And you want them to arrive at the train station at the same time, because if train B arrives there first, you have to call in your train station staff to process train B. Maybe there's like a gift shop and restaurants and sightseeing tours and whatnot. So you don't want to have to call in your staff for train B and then have to call them back later whenever train A gets there. Because in this situation, train A was delayed. Maybe they had some minor mechanical problems, or maybe there was a boulder from a rock slide blocking the train tracks and they had to move it. Either way, train B ended up ahead of train A. Train A travels at 20 miles per hour. Train B can only go a minimum of 10 miles per hour. If it starts going slower than that, then perhaps it just won't be as economical for the engines to run, or maybe it won't have enough speed to get up some minor hills. So train B needs to stop on the tracks and wait for train A. But if they stop for too long, then people are going to start getting bored just sitting there doing nothing. So train B needs to stop somewhere and just sit there and wait until train A is at the 1,000 mile marker, and then train B can take off at 10 miles per hour, and then both train A and B can arrive at the train station at the same time. As I explained in my other video, you have this one equation here. You can just rearrange it and put it in different forms, and you don't even have to know what it is you're solving for. Just look at what you have and plug some numbers into variables and see what pops out. In this case, we'll look at it as three separate machines. Here's a machine that says distance over time equals velocity. Bring your time up by velocity, and you'll have distance equals velocity times time. Bring your velocity under distance, and you'll have distance over velocity equals time. So we have three separate machines. Each machine can only take two inputs. Let's decide what two inputs we can plug in, and let's see what pops out. We have a distance of 1,000 miles. We have a velocity of 20 miles per hour. So that means we should use machine number 3, which is distance over velocity equals time. I like to set it up as a conversion equation, so units cancel out. 1,000 miles times 20 miles per hour. Set it up so 20 miles is in the denominator. The miles will cancel. And then what will pop out is your time of 50 hours. That means train A is going to be moving along this track for 50 hours until it gets to the train station. Now let's solve for train B. We now have a time of 50 hours. We have a velocity of 10 miles per hour. That means we can use machine number 2, which is velocity times time equals distance, or set it up as a conversion equation. The time is 50 hours, velocity 10 miles per hour. The hours will cancel, and you're left with 500 miles. That means train B needs to stop 500 miles away from the train station and wait for train A to reach the 1,000 mile marker, and then train B can take off at 10 miles per hour. Train A will travel at 20 miles per hour, and they will reach the train station at the same time. Now we have another situation here again where train A got delayed, traveling 20 miles per hour. Train B, we need to determine the velocity of train B. Train A is 1,000 miles away from the train station. Train B is now 250 miles away from the train station. But same situation, they both need to arrive at the train station at the same time. Let's look at your three machines here. Machine 1 has distance over time equals velocity. Machine 2, distance equals velocity times time. Machine 3, distance over velocity equals time. We have a velocity, we have a distance, so that means we need to use machine 3, plug in distance, plug in velocity. When we do that, we'll get 50 hours because I just solved that problem for the previous problem. Now We have a distance, 250 miles, and we have a time. Let's look at the equations here and see what we can use with a distance and a time. Distance over time equals velocity. 250 miles over 50 hours means that train B needs to travel at 5 miles per hour, and in doing so, it'll arrive at the train station exactly at the same time as train A.